Alright, let's take a look at the system. We got a two bucket system, two masses. They're connected by a rope over a pulley. That's a pulley. There's my rope. Here's my bucket one, here's my bucket two. Right off the bat, you can probably bet that bucket one is lighter or less massive than bucket two. Okay? Now there's a difference between mass and weight, whereas weight is the force of gravity pulling down on the object. The mass is just pretty much the measurement of how much stuff it's made up of. Here, let's go ahead and say that bucket one, this bucket over here, let's make it a 5 kilogram bucket. And over here, let's make this bucket let's make it twice as much. Let's make it a 10 kilogram bucket. Okay? And so, just using common sense, if you got a 5 kilogram bucket attached to a 10 kilogram bucket, well, this bucket's probably not going to be lifted up unless we pour in more stuff into this bucket, making it 10 kilograms or more. Then it'll be able to be lifted up. Okay, we got to apply more force upwards. And this is going to be the force of tension that's pulling up on it, the tensile force. Over here, it's the exact same force of tension that's pulling up on this one. Okay, the system's not accelerating. If it was, then it's going to be a little bit different, but right now it's not. And so right now, all we got to do is identify what's going on with this system. And so we're going to draw a free body diagram for each thing that's in my system that I can talk about. Here's a free body diagram of the 5 kilogram block. It's got the force downwards, it's got a force upwards, and whatever force is downwards, we're going to bet that it's going to be equal to the force that's upwards. It's going to be the exact same size. The force downwards is going to be the force of gravity, say Fg, the force of the weight, or whatever you want to say. And you calculate that by taking m times g. Okay, and so we'll do this just over here. I just want to set up these free body diagrams. The force pulling upwards is the force of tension from the rope. It's pulling up, and there is no normal force. There's no need for a normal force. It's not resting on a surface. So automatically, hey, if you thought, hey, there's a normal force pointing up there, it's not. And if you thought, hey, there's a natural force pointing up, then you fail. No. All right, over here. The free body diagram for this bucket, it's definitely got the force of gravity going straight down on it. Now this force of gravity and this force of gravity are not the same force of gravity. Okay, this is equal to mg, but it's a different m. This one's going to be m1g. This one's going to be m2g. It's going to be associated with the 5 and the 10 kilograms. Okay, over here we do have the force of tension pulling up. I'm actually going to make this dot a little bit bigger, because there's not just the force of tension pulling up here. There's also the force pushing up that's from this scale. This is a scale. So we need to draw that as well. And I'll say that's the normal force, not the natural force, but the normal force. Okay, the force that's perpendicular to a surface. The only way that the surface can push back is perpendicular to itself. Okay, so we have two forces pointing up, one force pointing down over here. We have one force up, one force down over here. And the key to this whole problem is that it is at rest. It's also at equilibrium. Okay, what does that mean? It means, hey, this thing's not moving in the first place, and all the forces are going to cancel out. There is no leftover force to give it an acceleration. It's nothing, right? And so we also don't need to worry about the x direction. We're only going to worry about the y's. So let's look at this 5 kilogram block or mass or bucket on the left side. And let's talk about the sum. This is sigma. It's going to represent the sum of a bunch of somethings. And here it's going to represent the sum of the forces on this object in the y direction. It's just a formality that I'm writing down the y. Well, we want it to be equal to 0. It's equal to ma, but we want it to be equal to 0 because it's not going to be accelerating. It's in equilibrium. And the forces that we have are two of them. We have one force up, we have one force down. We have tension pulling upwards, and we have this mg going down. Let's see, it's going to be 5 for the m, g, let's call g 10. Now let's just say force of gravity is going to cause an acceleration that's equal to 10 meters per second squared. And usually it's 9.81. It's just easier to make it 10. It's all right. So 5 times 10 is going to give you a 50 Newton force straight down. And if this is equal to 0, then tension has to be 50. So tension is equal to 50 newtons. And tension here on this side is pulling up. Interesting thing about tension is that sometimes it can pull one way, and then the other side on the other object that it's attached to is pulling the other way, which is happening here. Okay, well, that's all for that side. And yeah, there's another picture. Over here, we can say the sum of all forces in the y directions equal to nothing, because we don't want any leftovers. And let's count the forces. We have 1, 2, 3, 3 forces. 2 of them are up, 1 of them is down, so 2 of them have the same side. Could be negative, could be positive. Let's make these positive. This will be our negative force, mg going down. So we've got tension and this normal force minus mg going down. Now this m is going to be 10. 10 times 10 is going to give you 100. And there we go. Now, we got to figure out what Fn is. What is normal force? What is this scale going to read? Scales read you the normal force, how much they're pushing up. Well, do we know tension? Yeah, we do. We just figured it out. And for a system that's in equilibrium, tension over here will be equal to tension over here. If it's accelerating, then I don't know. Maybe not. Probably, but we'll just be careful. Here's tension, 50 plus normal force minus 100 is equal to 0. And if we just do some mental math right here, if this plus this plus this is equal to 0, what does normal force have to be? Well, it's got to be 50, right? 50 plus 50 is 100, minus 100 is 0. So normal force here is equal to 50 newtons. And that's right here, this normal force. Okay, that's not that bad. If this bucket weren't here, the normal force would be equal to 100 newtons. But the bucket is there, so it's pulling up on it. There's tension, so 50 newtons is what's required of normal force. Normal force will scale, and it's going to scale to whatever it needs to be. If we're pushing down on this bucket, normal force is going to get bigger. If we're pulling up on this bucket, the normal force is going to get less. Okay? If we push to the side, the normal force doesn't change because normal force is in the vertical in this case. All right. Over here, we got this guy with a lawnmower. Check it out. And if I were to draw the free body diagram of this object, we have the force of gravity going down. And I didn't give a mass, which was stupid of me. I'm going to say it's going to be a 20 kilogram lawnmower. And we're going to have this guy pushing down at this angle. And I didn't even give that force either. Also negligent of me. Let's say he's pushing with a force of 100 newtons. To make it easy. Okay. And we're in 2 dimensions. We're working with vectors. So let me draw my axes there. Let's give this angle, let's make this angle like this is 35 degrees. There we are. But those aren't the only 2 forces that are there. They better not be, you know, because we probably got some friction. Probably got some friction going back this way, and we can calculate friction, or we can just give it. In this case, we're just making up the problem. Let's say friction is 50 newtons. How about that? Just making it up. Well, we got 1, 2, 3 forces kind of downwards and or this way and this way and this way, and we probably need a force pointing up. What is it? It's the normal force. Please say normal. Don't say natural. Normal force, it's going to go up, and it's the only force pointing up. What does that mean? It means that any force that's pointing down, any component of a force that's pointing down, normal force is fighting that. So here are my vectors. I have 1, 2, 3, 4 vectors. And this vector is the funny one because it's at an angle, which means it has these components associated with it. And we're going to have to deal with that. So how do I find, if this hypotenuse is 100, I need to find this side, I need to find this side. let's work with this side first. This is the side that's opposite my angle. This is my hypotenuse. Opposite hypotenuse, that's going to be sine. And so I'm going to take 100 times the sine of my angle 35, and I'm going to get something. My paper just messed up. I'm going to get 100 times the sine of 35 gives me 57.36. 57.36 newtons. And if that's sine, I'm going to take the other side, which is going to be 100 times the cosine of 35. And I'm going to get 81.92 newtons. And if you're not quick with the tangent, cosine, sine, how to find whatever component that we're looking for, it's going to take you practice. There's no other way to say it. A lot of you guys just like to watch things, look at things like this video. You're just going to look at this video but not actually practice it. Practice it. You know, pause the video. Actually try to do what I'm doing right now before I do it. But here are the components. And what we need to look at is, you know, what cancels out, what doesn't. And we're working with 2 dimensions, so let's go ahead and work with those 2 dimensions. And we can sum up all the forces in the y direction. We can sum up all the forces in the x direction. And there's one guarantee. In the y direction, this vertical here, we don't want any excess force. This lawnmower is not going to go floating off. This lawnmower is not going to go through the ground either. We want this lawnmower, we want this guy to get paid. He's going to go straight across. And so the sum is going to be 0 here. And how many forces do we have? I see 1, 2, 3 in the vertical. And let me say, oh, Fg is going to be 20 times 10, so 200 newtons. And let's say upwards is positive. So we have normal force minus 200 minus 57.36 newtons. And this says that if normal force is the only positive thing, these 2 things combined, 257.36, that better be normal force. And it is. 257.36 newtons. That's going to be our normal force. So, no problems there. In the x direction, it's probably the more important one right now. We don't know if the sum of all forces in the x direction is 0. We don't actually know that. Most likely it's not. So what we're going to do is we're going to look at these forces. We're going to say we have how many forces? We have 2. So actually we do know. 81.92 is going to be our positive minus 50. Well, what's that equal to? Take 50 away from 80. That's going to be 30. So 31.92 newtons is our leftover force. Which way is it? It's to the right. So what is this thing going to do? It's going to accelerate to the right. And this is called the net force. All these things involved here, all these components, all these pieces, you know, it's like, you know, you get paid a gross amount, a gross salary, and it's an awesome number. You get paid, you know, your check comes in, it's $500, it's $1,000, and then it says, oh, we need to pay for taxes, we got to take out all these other things. Oh, here are some charges, here's some fees, here's the net, here's what you actually get, and it sucks. Here's what we get. We started off with 81.92, friction took away 50, and we end up with 31.92. That's going to be the net force, and that's going to be equal to MA, and M in this case is 20. A is what we don't know. And so if we look at this, we have 31.92 is equal to 20A. Solving 31.92 divided by 20 is equal to, let's get it nice and exact, gives me 1.596. And that's acceleration meters per second squared, which says if we continue to push and exceed this frictional force, we are accelerating at a rate of 1.56 meters per second squared, which means this guy better start running. That's alright. Okay. I'm going to stop this video right here.